Then the next thing, the third thing we did, we said, okay, we're going to assign these things called oxidation numbers. Well, they're actually charges if they're ionic, but there are some different things when you take a look at an overall equation. Okay, so I'm going to do the first one, and I'll call on some volunteers to kind of share what they have for charges on the other ones. Okay, Ag is a plus 1 oxidation number. Now, the ClO3, this is where some students were struggling with this. And so what I do is I just pull ClO3 out, and I know it equals a -1. How do I know it equals a -1? Where do I look?
On the sheet.
Yeah, on your polyatomic ion sheet. So oxygen, I'm just going to give totals from now on because I'm not going. I think everybody knows how I get this -6 total, right? Okay. So then, what does chlorine have to be? Positive what? 5. So chlorine's a positive 5. So I go positive 5 and I go -2. Now, when I write them above there, I'm not going to write the total. I can do that in another spot. I just want to write their individual, what's called oxidation numbers. Their individual oxidation numbers. This is a +1, this is a -1, and this is 0. Some students on that quiz we took, if an element's by itself, they were looking up the charge and they wrote a -2. It's not a -2 unless it's bonded to something. Does that make sense? Okay, so we're gonna dissect this a little bit more because I'm going to add a little bit more to this assignment. And so we might look at the previous 2 examples to do what I'm going to talk about. So this last concept, before we start doing some labs, and we'll do a lab tomorrow, we're going to look to see where what we call an oxidation number changes in value from the left side to the right side. It's pretty easy once you put the numbers up there. So let's look which elements change their value from left to right. 2 of them did. And you'll always have 2 of them if the charges are different on both sides. So if the charges are different on, this is the reactant side, this is the product side. The right side's a product. So what I just like to connect them and kind of show, well, those 2 are different. What other 2 are different? Okay, oxygen's different. Okay, what happened to cause chlorine to go down to -1? There must be a reason. What's that? Well, we automatically match silver, but that's not the reason. I mean, silver is still going to be a +1 no matter what chlorine is going to be because they are independent of one another. Because silver doesn't change its charge. So, what creates a charge in an atom? Electrons and protons. What can leave the atom? Electrons. Okay? So the only thing that can leave the atom is electrons. So that's the only thing that can create a charge difference. So are chlorines being added to this chlorine, are electrons being added to this chlorine here? Or are they taken away? That's what you have to decide. So electron is negative. Okay, that's the key. Some students mess this up because they think add, is kind of opposite of our thinking because electrons are negative, and when you add electrons, basically what happens to the value of that oxidation number? Does it go up or down? If you add electrons or negative value, it goes down, right? So what happened to this chlorine? Its value went down. So we call that reduced. Does that make sense? Reduced? When you reduce something, you lower its value. I'm going to reduce the value of this. Hey, I'm going to ask for $4,000 within my vehicle, but hey, you know, I'm not selling it. I'm gonna now reduce it to $3,500. Reducing means lower in value. Does that make sense? So that chlorine's reduced. Now, this term, and I'll give you the definitions for these two in a second. The next term, what happens to the oxygen? It goes from a -2 to 0. So it goes up in value. Right? It goes from a -2 to 0. So is it losing electrons or gaining electrons? Losing electrons. It's giving electrons up. Guess where the electrons went? To chlorine. Chlorine gained them. Okay? So this is oxidized. We call it oxidized. Have you guys ever heard the word oxidized? In what way have you heard Huh? Could be rocket fuel oxidized. That is an oxidation type of reaction. Rust. If something rusts, iron rusts, that means it's oxidized. It means that it goes to a different charge that's higher. Okay? So off to the side, I don't know where you want to put this. This is just real simple notes. Oxidized, or oxidation we'll say, and reduction, meaning reduction means gains electrons. And oxidation means it loses electrons. Okay? So oxidation loses electrons. And reduction means gains electrons. This is called a redox reaction. What's it mean by redox reaction? Well, that means you have something, they just shorten it. It's called oxidation reduction reaction. But a redox reaction is one where you have electrons move. That's all it means. Electrons move from one thing to another. Okay? Now to balance it out, you should have had a 2, 2, 3, because you were supposed to do both. Any questions on that? Okay. All right. So ask for a volunteer for number 4. Somebody give me the value. Go ahead, Billy.
The value for what?
For all of those above, the charges.
Plus 3.
Okay, this should be a 0.
Oh, because it's by itself.
Yeah, there you go. That's okay. Hey, guys that willing to volunteer to give answers, you know, you're just starting to do these, and we're starting to try to get rid of some things, bad habits. We're bringing in a concept like aluminum. We always made it a plus 3. Well, over here it's a plus 3, right?
Yeah.
Okay. So then H, what'd you get?
For H, I got plus 1.
And chlorine
Minus 1.
and hydrogen.
0.
Okay. So then what we would do is we'd say, okay, what's changing in value? Oh, chlorine's a minus 1. Thank you. Sorry. So what's changing in value? Aluminum and hydrogen. So is aluminum oxidized or reduced? Oxidized. Very good. And is hydrogen, well, if aluminum's oxidized, the other one has to be reduced. Okay, so once you find one, whatever you feel that's easier to determine, I think oxidation is probably easy. Well, I think reduction might be easier to determine, I think. And so hydrogen goes from a plus 1 to 0, means it lowers in value. So that one's reduced. Okay, and then to balance that, you would put, I believe it's
2623.
2623, is that what it is?
Yeah.
Okay. Now, something you guys don't need to do. I want to show you something though with electrons. Okay, so this example, I want to just show you. Now I won't do that now. I think that's enough information that you guys have. So, why don't we do this? I don't know why I got 5 and 7 there. It should be 5 and 6, shouldn't it? Unless I got my numbers wrong.
The numbers are mixed around on the worksheet.
Is it?
Yeah.
Did I go 5 and 7 on the worksheet too?
Yeah.
Okay, that's fine. So, if you've got the charges above, then go ahead and find out which one's oxidized, which one's reduced. Okay, so I'm going to give you probably about 5 minutes to tackle at least 5 and 7 and write their oxidation numbers above them if you haven't already done so. If you've written above them their oxidation numbers, then you can just draw lines to the two that change their value and then decide if it's oxidized or reduced. Okay? So I'm going to give you about 5 minutes to do that. See if this makes sense. On this one here, aluminum 0. Those are the fun ones. You don't have to look them up. Okay? And then lead. Lead is dependent upon how many nitrates we have. Nitrates overall charge is a -1, which makes it a -2. So lead should be a +4. Or not +4. Sorry. +2. Okay? And then aluminum here is a +3. I'm going to take NO3 out. And I'm going to just treat it like a polyatomic ion. I think it's easier to do it that way. Some of these, you have multiple ones like this. So if you take it out, it's easier to handle. And so it should be a +5 on both sides for the nitrogen. And then oxygen's a -2. Okay, so that's kind of what it should look like. So aluminum is changing in value. What's happening to it? Oxidized. Okay.
Are you just showing us like what it like ends up being like oxidized or reduced, or do we actually need to write that out on each one?
I would like you to write it out on each one.
We want, okay.
Yep. So that you have it and you're doing it, actually doing it. What's the other one that changes? Lead does, right? You see how it goes lower in value? So lower in value is reduced. So that's reduced. How many electrons did it pick up, by the way? 2. How many did aluminum lose? 3. Ever see why aluminum lose 3? So that when we balance this, it should make sense on electrons got to be conserved too. So what I mean by electrons got to be conserved, I mean electrons lost and gained have to equal one another. And so what we'll put is a 3 here and a 2. Well, I'll put a 3 here. And then put a 2 here and a 2 here. And that's balance it, right? Now, 2 aluminums lost how many electrons each? 3. So that's the total. How many electrons was lost? 6, right? Each aluminum went from 0 to +3. So each aluminum lost 3, which is a total of 6 electrons. Guess how many lead gained? +2 to 0. Each lead gains how many electrons?
3, 6,
2. 2 to 0. If I go 2 to 0, how many electrons do I need to add to get that 2 to 0? Got to add 2 negative ones. It makes a -2. So if I send 6 to that lead, it takes care of those 3 that go over. Okay. Next one. This was a +5, right? -2, +1, -2, +1, +5, -2. There's no, that's not a redox reaction. Does it make sense why it's not? Are the values any different on the right than the left? So if you get an equation that we have no change in values on right or left, we don't call that a redox reaction. And we will not draw arrows. Because there's nothing to draw lines. There's nothing to draw lines to. Make sense? Okay, and in the balancing of that, some people, I know there's about 3 or 4 people says, I can't balance that. I mean, it's like, okay, there's 4p, there's 1p, I put a 4 there. Okay? There's 10 oxygens and there's 1 oxygen. I'm going to leave oxygen and balance it out last. Some people get to go to oxygen and go, I don't know. Well, don't do oxygen because oxygen's in 2 places over here. Leave it to the very end. Don't tackle in order. Well, let's go to hydrogen. So how many hydrogens are here? 12. And how many's here? 2. Put a 6 there. Now I look at oxygen. Guess what? Voila. It's balanced. So a lot of times your last element balances it out. Okay? So your last element will balance out. All right, what I would ask you to do is, I just think you've got 2 more to do, right? 8 and 9?
Yeah.
So you just do 8 and 9, your name on that. I'll balance 8 and 9 just so that you guys can see those at work. So pretty much we'll have done all this one other than you guys putting in your oxidation numbers and then connecting them. So H, I'm going to put a 2 here, balance my H, Cl balances, Ba balances, and my water, I've got 2 hydrogens and 2 hydrogens, which is 4, but I also have just 2 oxygens, so what do I need to put in front of this? 2. So that balances. Okay? Now some of you guys that write down below, keep doing that. I leave the space. You want? I think some of you don't have to do that for every one. Some of you, like every single one, you write it down. And for some of them, they're so simple to balance that you don't have to do that. Okay, this last one. In H3, there's 1 in. I'm going to put a 2 in front of this. So that gives me 6 hydrogens. I'll put a 3 in front of this. And my oxygens don't work. So what do you think a little trend we use to make sure that... Double them. Yeah, just double them. Say, okay, I'm going to go ahead and put a 4 here, and I'll put a 6 here. Okay, I'm just going to double them. If you double them, then that takes care of that even-odd situation. And so now I put a 2 here, and a 3 here, and we're good. Okay? It's okay to double them, and then a lot of times that takes out that, makes that ratio whole number. Okay. All right. You will finish that up, put that in the tray later. I'll just have as a completion. I'll look it over, see how you're doing.